glad you're coming in, Miss Thornton, so that you can not miss that and get behind. Frustrated to get behind. Okay, I want to do a quick review. And I want to start here by talking here about the electrolysis of water. And I want to review this because yesterday I made that mistake in the notes. It took me a while to figure out what I had done wrong with the equation. I had misbalanced it. And I found just an easier way to explain this. So just want to review it real quick. And then we will proceed into the next part. Electrolysis of water, we know, basically involves splitting water into hydrogen and oxygen. And it always is going to involve a battery, which is, in this case, run into two test tubes. And those test tubes are submerged in a beaker of salt water. And we can't use just pure water. What's the reason? Why do we have to have some ions present? Right, we got to have ions must be present to conduct electricity in solution. So ions carry charge. So ions must be present to carry charge through solution. So ions must be present to carry charge through solution. That's why the NaCl, the salt, is present in this. Now we said that we filled these up to the brim with water, and when this reaction starts, we start to get bubbling take place off of both of these electrodes, which are just pieces of wire stuck up inside of these test tubes. And now we got to figure out what are the half reactions that are taking place, and we have the saying red cat and anox still applying for this, which means reduction that takes place at the cathode, but the signs are different than in a voltaic cell. For the cathode, what is going to be the sign of the cathode for an electrolytic cell? Negative. Very good. And for the anode, that has to be positive.
So in a voltaic cell, the anode is negative?
Yep, cathode is positive. You got it. So if we were to look now and see which one is oxidized, the reaction that is oxidized is what we went over yesterday. It is two water molecules break. This is in the liquid phase to produce oxygen gas, 4 protons and 4 electrons. That's what takes place at the anode. And over here at the cathode, to simplify this from yesterday, we can simply use this equation. 4H plus 4 electrons yield 2H2. Okay, hold on for just a moment because I want to put them together and I think it'll make a little bit more sense. So here's what's happening. When you force electricity through the water, it is actually breaking apart the water to produce oxygen gas, 4 protons, and 4 electrons. Now what happens, this takes place at one terminal, and it's the one that's connected to the positive terminal of the battery. So right here, this is filling up with oxygen. Now these 4H plus are ions. They're able to move through solution. So over here on this electrode, those 4H plus meet 4 electrons, which are carried through solution by ions, and form hydrogen. This takes place in the negative terminal that's connected to the battery. If we add these together, 2H2O liquid yielding O2 gas plus 4H plus 4 electrons, and we add that to 4H plus 4 electrons yield 2H2. We're able to cross out our electrons, cross out our protons, and we end up with our total equation as follows. 2H2O liquid yields O2 gas plus 2H2 gas. And this is what we call our complete equation. We usually write electricity over or under the arrow to show that it requires a continuous input of electricity for this to occur. And you will notice that you get twice as much hydrogen compared to the one that is in front of the O2. So when you did this in lab, we saw that one of these bubbled pretty rapidly where the other one did not. And the one that was bubbling more rapidly was the hydrogen compared to the oxygen. So the splitting apart of water in the overall equation to produce oxygen gas and hydrogen gas is called electrolysis. These are the two half reactions that occur. This is the overall.
So is it the same thing every single time?
Same thing every single time. Yes, it is. Yep. That's the same thing every single time. Okay, now the next thing that we need to talk about is what is called electroplating. And electroplating is a very similar process to electrolysis because it still uses an electrolytic cell, but it has a different purpose to it. The purpose of electroplating is to take a very expensive metal. So in this case, we're going to use silver. We're going to take that silver and we're going to connect it to a battery. Remember, electrolytic cells always involve a battery. Getting this, Krista? We are going to take and we're going to now connect a wire to whatever we want to plate. And in this case, we're going to plate a spoon. We're going to make some silverware.
So don't we make a fork? Isn't that easier to draw?
Do a fork if you want. Put a fork in it. Sure.
So why is the spoon, does it matter that the spoon is submerged or did you just?
You have to submerge it.
Okay.
And you're going to submerge this in a solution. We're going to use AgNO3 aqueous. You have to submerge it in a solution that has, this is important guys, you have to submerge it in a solution that has the same ion as the metal that you're trying to plate. So it has to have silver ions present in the solution.
Why did you put the positive?
Yeah, I'm really glad you asked that. Silver is way down here at the bottom of table J. Lithium's up at the top. Normally, electrons want to go from lithium down towards silver. Well, in electroplating, we have to do it the reverse way, correct? So here's what happens. We've got to take electrons, and we've got to get them to go over here to the spoon, and the spoon is initially made of iron. All right, that's what most cheap silverware is going to just be made of iron. Well, I'm just going to call this iron up here to make it match our diagram. Iron is above the silver, so what is going to want to make the electrons leave a low reactive metal and go to a high? You've got to place the positive terminal of the battery so it attracts the electrons, or you can think of it this way. The positive terminal of the battery pulls the negative charge toward it. Then once it goes through the battery, the negative side of the battery pushes the electrons and repels it down onto the spoon. That's why the positive terminal gets connected to the anode. All right, and remember, the anode is where what takes place? Oxidation. But that's only true for an electrolytic cell. We always call the anode positive for electrolytic cells. We call the cathode negative for electrolytic cells.
So
Okay.
Lower on table J is
For electrolytic cells, yes. Does anyone have in mind how the half reaction will look for silver? Yep. Yields Ag plus 1 electron. That is the half reaction that will take place, and the silver will actually turn into silver ions as it goes off the electrode into the solution. All right, it's going to go actually off the electrode into the solution, turning into silver ions. It's going to go up. The electrons will go up and get basically pushed onto the iron spoon. And here's the thing that everyone gets wrong. The iron is not a part of this half reaction. On the other side, all you do is take the one reaction you wrote in terms of oxidation and reverse it to write it in terms of reduction. Can someone give it to me?
Ag plus 1 electron yields Ag.
That's it. You take the reaction that you just wrote and you reverse it. And what happens is a very thin layer of silver plates itself to the iron spoon, and it gives the appearance of a pure iron piece of metal, but it's only plated. Say it again, Zoe. Great question. This is the oxidation half reaction. This is the reduction. So we've got to add them together to get the overall. Can someone do it?
Cross out your electrons.
Very good.
So we get Ag plus 1 yields Ag plus 1 plus Ag.
Right. So what you're going to notice here is that the overall reaction generally isn't even written because it looks like nothing took place. It does make sense. You can see why it occurs. And it does, and this is a very, very important industry. This is, again, how you produce chromium products, how you have gold-plated jewelry, silver-plated jewelry. A whole lot of applications involve electroplating, not just jewelry, not just decorations. The ion, this Ag plus right here, Zoe, is part of that solution. Okay? The iron is simply a holding place for the electrons to be housed on to meet the iron, or the silver ion.
So we don't write that.
You do not write iron. You will never write the cheap metal in this process.
How long does this process take place? Like how long
Well, we're going to do it in lab, and we're going to do it in a period where we're going to basically coat something. But I think that's actually a really good question for your dad, who worked in that field. I don't know, like if you were to plate, for example, like a car bumper, chromium plate it. I don't know the time period, but it's not an absorbent amount of time. Usually it can be done, the process can be run in 30 minutes. The correct answer to that, in AP chemistry, what we do is there's an equation that allows us to calculate how long it will take using current, which is coulombs per second, and we can calculate it. So I do know for some things how long it would take, but to do like an industrial sized application of it, that's a good question for him. Yeah. Someone else have a question? Okay. Now, what I'd like you to do is pause there and go to your homework. Because on your homework, you had this picture. It says, use the following picture to answer the following, and you're electroplating a fork. And I just noticed something in this picture that I need to add. Sure did. I forgot the battery, which, if I forget the battery, this whole thing will not work. So, yours does have a battery? Okay, good. I probably just had revised it. Let's take a look now at your homework and see if you were able to get this right. Does anyone want to actually pause, though, and see if you can write those half reactions before I go over it? Now that you've seen an example. Go ahead and do so. Give you a second here to do that. And see if you can make a correction with it, and then we'll go over this. Remember, you do not care about the iron part of the fork, meaning you will not use Fe in that half reaction. If you find yourself using Fe, you're doing the wrong things. You don't use Fe there.
Is the charge +1?
For gold, we're going to use gold 2. So, okay. Do it for me tomorrow and let me know.
Well, Okay, because I labeled all of these silver. That's what I did.
Well, I may be wrong. I thought gold could have a charge plus 2,
So I guess you better do.
but I could be wrong. You could do +1 on yours if you want. It's going to be pretty similar. That's what they were just saying on their table. I'll change mine. I'll change mine to gold +1. Sorry, Jess. They'll typically tell you or pick the first one. Yep. Okay. If we jump down and look specifically at this problem, it says determine the anode and the cathode. Now, for an electrolytic cell, the anode is going to be the one at the bottom of table J. That's exactly the opposite of what we talked about with voltaic cells. So the anode is the gold, the cathode would be the iron or the fork. Your oxidation half reaction would be AU yields AU plus 1 electron, and then AU plus 1 electron yields AU for reduction. Hopefully you can see that your anode with the gold is on your left. Electrons are being driven off of that and forced onto the fork, where they may meet gold ions in solution, and they will plate themselves onto the fork.
Your fork isn't submerged either.
I only plated half of it. I plated the bottom half. Thank you. That would be a very funny looking fork.
No, I'd just be like,
It would be kind of cool. It'd be like half iron, half gold. Okay, number 1, describe the difference between a voltaic and electrolytic cell. Main differences. First of all, which one is spontaneous? Voltaic. Electrolytic is non-spontaneous. The other big difference is what value you assign to the cathode and anode. The cathode for a voltaic cell is positive. The anode is negative. Switch them for the electrolytic cell. Okay, tell me the purpose of the battery. Caleb, go ahead. What is the purpose of the battery in an electrolytic cell?
Because the reaction isn't spontaneous.
That's right. So the battery is used to provide energy to force a non-spontaneous reaction to occur. So it forces electrons from the least reactive to the most reactive metal. And number 7, we can skip to. Why is electroplating beneficial? Well, first of all, it allows you to cut down the cost of making things look really nice. For example, if you want to gold or silver plate something, you can save with the price. A lot of jewelry is made with electroplating, but also, we haven't talked about this one yet, but corrosion prevention. If you can take a metal that doesn't corrode as easily and put it over iron, which corrodes very easily, you can help to cut down on the corrosion of metal. And that sounds maybe not like a big deal, but corrosion prevention is a very, very, very important thing in America in terms of transportation. Think about bridges, just really quickly. Bridges have a lot of metal, and they have to be systematically checked to see if they're corroding, and if they're corroding, they have to be repaired. The United States spends billions of dollars a year to fight corrosion, to keep the American transportation system moving. Number 8. What is the splitting of water according to the following equation called? And hopefully you have electrolysis. You needed to draw a picture of this. I drew my battery off to the side on this one, but you should have it coming in looking like this. And I had given you two reactions that you can use instead of the ones I listed here. The first one here for the hydrogen, the simplest way to do it is 4H plus 4 electrons yield 2H2. And for the oxygen, 2H2O yields your O2 plus 4H plus 4 electrons. You can use the ones we talked about yesterday in the notes, or these. They're really the same equations. Number 10. Will the hydrogen oxygen have the greater volume when the water is split? Which one has the greater volume? hydrogen for sure. According to our net equation, the final product yields 2 hydrogens for every 1 oxygen molecule. So we get twice as much hydrogen. Number 11, what happens to the water in these test tubes as the gases bubble up? Yeah, we force the water out. All right, so we displace the water and replace it with oxygen. And number 12 is electrolysis, a non-spontaneous reaction. What does that mean? It absolutely is, and it means it will not happen without a continuous input of energy. It doesn't happen without a continuous input of energy. Okay, what I'd like you to do is to go ahead now and pull up the electrolytic worksheet 2, and we're going to do it right now in class.